Welcome to the solutions to homework set number 7 for ECE 341. This homework set looks at uniform and exponential distributions. Now the first problem says suppose I have two uniform distributions. A is uniform between 0 and 3. B is pick a random number between 0 and 5. What's the distribution of A plus B? Well, to do that, a couple ways. Convolution, or in the Laplace domain, multiply. So take the moment generating function, also known as Laplace transform. This is A of t, the Laplace transform. So this is a step at 0 minus a step at 3. Height has to be 1/3 for the area to be 1. This one, the height has to be 1/5 for the area to be 1. Area must be 1, and that's a minus sign. So here's the second Laplace transform. Multiply the Laplace transforms, that's convolution in the time domain. And basically, multiplication is way, way, way easier than convolution. So multiply all these out, I get 1 over 15s squared. Multiply these out, I get 1 times 1, 1 times e to the minus 3, 1 times e to the minus 5, e to the minus 3 times e to the minus 5, exponents add. So there's your answer. 1 over 15s squared is 1 over 15x times u, delayed by 3, delayed by 5, delayed by 8. So at t equals 0, this one kicks in. At t equals 3, I get these two. So it's x minus 3. At t equals 5, these kick in. And t equals 8, all of them kick in. So there's your answer. Second way to do this is use convolution. This is where MATLAB kind of helps. I'll input correcting that. Input a step function for A between 0 and 3, step function for B between 0 and 3. Y is the convolution of A and B, and here you're actually integrating, so you have to multiply by dt. And just so I can plot it, let's limit y to have the same length as t, and then plot it. Here's what it looks like. So same answer we got before, and the area under the curve has to be 1. And you can check that if I do what is the sum of y times dt. This adds up a bunch of rectangles. Width times height is area. Add them all up. I should get 1 if I did this right. And you do. So the second way of doing it. Third problem. Suppose I have this circuit. What happens if I actually build it? Now, due to tolerances, the resistors are nominally 1K, 3K, 4K, 1K. If you have 5% tolerance, it's going to be 1K plus or minus 5%, 3K plus or minus 5%, and so on. So because that variation, y is going to have some distribution. Find that distribution. So what I can do is first come up with the equations. X is minus R2 over R1 times 2. Y, this is a non-inverting amplifier. Gain is 1 plus the ratio, 1 plus R4 over R3. Multiply it all out. Y is minus R2 over R1 times 1 plus R4 over R3 times 2. Depends upon what the resistors are, tells you what y is. So let's do a Monte Carlo simulation. I'm going to pick 1,000 values. For each iteration, I'm going to take 1,000 ohms plus or minus 5%, 3K plus or minus 5%, and so on. Once I pick the resistors, kind of like grab resistors out of a bin, find the voltage at y. Save them. Then when I'm done, find the mean and standard deviation. Now ideally the voltage at y should be minus 30 volts. Because of variation, it isn't always minus 30. Here on average it's minus 30.06, and the standard deviation is 1.59. I can see what the CDF looks like. If I sort P and plot it, this is probability, here's the voltage. So there's a 20% chance the voltage will be minus 3.35 volts, no, 3.45 volts or less. 60% chance the voltage will be right here. 90% chance it'll be to the left of that point. There's your CDF. Save that. Once I have the CDF, I want to find the PDF. What's the distribution of y? If I differentiate that, in theory I get the PDF, but there's noise on it, so it's hard to differentiate. Later on, we're going to do curve fitting. Curve fit that with a normal distribution, curve fit that with a Weibull distribution. Problem 4 and 5 skip. Those are Pascal distributions. That's tomorrow's lecture. The last one is queuing theory. Suppose I have customers coming to a restaurant. They arrive at the restaurant with an exponential distribution with the mean of 50. So this is the arrival time. It's exponential, and e to the minus t over 50 divided by 50. So that's the PDF. This is how long it takes to serve the customer. Once they place their order, like if you're at Wendy's, some restaurant, it takes a variable amount of time. Suppose that's also exponential, e to the minus t over 40 times 1/40th to make it a valid PDF. Okay, so there's a couple things to calculate first. Come on, erase. The first thing is the arrival time. That's an exponential distribution with the mean of 50. So that's what these guys, exponential mean of 50. That's the time between customers arriving. The time that a customer arrives is the previous time, so if the door is open at 0, 58 seconds later, the first customer arrives. 20 seconds later, the second customer arrives. 66 seconds later, the third arrives, and so on. That's when they arrive. The service time nominally is the time that you arrive. If there's no queue, we're going to change that in a second. Once you're served, this is how long it takes to serve you. You got to place your order, like you go to Wendy's, you got to place your order, large order, fries, Pepsi, Coke. This guy is also exponential, so this is 40 seconds, it equals log of 1 minus p, also an exponential distribution. The time that I'm done is the time that I'm served, plus how long it takes to place the order is the time I'm finished, and so on. The oddity is this guy right here. The time that I'm served is the maximum of the time that I arrive and the time the previous customer is finished. So if I arrive at 78 seconds and the customer is still getting served, I have to wait until they're served, then I can, or wait till they're done, then I can be served, or place my order. So this is actually max function, max of c and the previous f. So once I do that, this is the time that I'm served, plus the time it takes to finish is when I'm done. The wait time is the difference between the two. So here I had to wait 0.64 seconds right here at entry 14. I arrived at 292. I didn't get served or didn't get to place my order till 406, so I waited 114 seconds. That's the wait time. And the queue size. If I look at when I arrive, like let's take one like right here. I arrived at 472 seconds. The previous customer is still there. The previous customer is still there. This customer's left. So I compare when the customer is done versus when I arrived. How many customers have the done time greater than my arrival time? That's your queue size. So once I set that up, I can copy this in Excel. And once I'm done, kind of go through it, I run this for 1 hour, so 3,600 seconds. The maximum queue size is this column right here. Which one's the biggest? So there's 443, well, this is the wait time. So that's about the longest wait time, 443 seconds. The biggest queue size is, go to the last column, biggest queue size was right here. So at this point, I arrived at this time. There are 9 customers who finished in time right up to here after I arrived. So I'm the 9th person in line when I come in the door. What restaurants do is if the queue size is too large, then people will turn around and walk out the door. That's lost revenue. If the wait time is too large, then customers get frustrated and leave. So what happens is if this gets too large, I'll add more servers. And what that does is that reduces the service time. If, on the other hand, I have numbers that are fairly small, I can have people go on break, send people home. I don't need as many servers. And it's kind of a balance. I want to have enough servers to keep the queue size, the wait time down, but not too many servers because that wastes money. And that's an area called queuing theory. It relates to exponential distributions. So that is homework set number 7 in ECE 341.